So there will come a time when you're asked to interpret a blood gas analysis. So in other words, an arterial blood sample will be drawn from your patient, and from the various measurements that are returned back to you, you will have to figure out what type of acid-base disturbance exists, if any at all. And the idea being that certain acid-base disturbances will point you towards certain sets of diagnoses. And why do we care about figuring out what type of acid-base disturbance exists in our patient at all? Well, if we can figure out what is going on physiologically, then this can inform which diagnoses we should consider as part of our differential. Now, there are four main acid-base disturbances: metabolic acidosis, respiratory acidosis, metabolic alkalosis, and respiratory alkalosis. And each of these disturbances has a corresponding pH, partial pressure of carbon dioxide, or PCO2, a particular concentration of bicarbonate, and what is called a compensatory response. Now, before we go into the corresponding values for each of these acid-base disturbances, it's helpful to understand first the buffering system of the body. Recall that carbon dioxide and water form carbonic acid, which is in equilibrium with bicarbonate and hydrogen ions. And a change in the concentration of any of these reactions will affect the direction that the reaction goes in. Now, at a pH of 7.4, which is around the normal pH of extracellular fluid in humans, the ratio of carbonic acid to bicarbonate is about 20:1. So a change in the ratio of these ions will alter the pH, and this leads to an acid-base disturbance. And already you can start to see some of the factors that I mentioned earlier. The relationship between pH, PCO2, and bicarb concentration is modeled in the Henderson-Hasselbalch Equation, which, if you recall, is pH equals negative log of the hydrogen ion concentration, which equals pKa plus the log of the bicarb ion concentration over 0.03 times the partial pressure of carbon dioxide. So pH is intimately tied to two components: the concentration of bicarb ions, which is the metabolic component, and the partial pressure of carbon dioxide, which is the respiratory component. And the two organs that play the main roles in acid-base buffering are the lungs and the kidneys. The lungs control PCO2, which is the partial pressure of carbon dioxide. And I think it's helpful to think of carbon dioxide as an acidic entity. So as PCO2 increases, the pH decreases or becomes more acidic. And vice versa, if the PCO2 decreases, the pH will increase or becomes more basic. And the way that PCO2 is altered is with basically how fast or slow you're breathing. Now, the kidneys help to regulate the concentration of bicarb ions. And you can think of bicarb as a basic entity. So as bicarb increases, the pH increases or becomes more basic. And as bicarb decreases, the pH decreases also and becomes more acidic. So with all this in mind, let's walk through each of these examples of acid-base disturbances. Oh, but before we do, I think it's helpful to have the normal values for each of these parameters in mind, just for reference. Normal pH is between 7.35 to 7.45. And normal PCO2 is 35 to 45 usually, and the units are in millimeters of mercury. Normal bicarb concentration is around 22 to 26, and those units are in milliequivalents per liter. Okay, so let's start with metabolic acidosis. We know that the pH in metabolic acidosis is going to be acidic, or less than the lower limit of normal pH, so less than 7.35. And since it's metabolic acidosis and bicarb represents the metabolic component, we know that this too will be decreased. And in metabolic acidosis, the lungs can immediately respond by increasing the ventilation rate or hyperventilating, which leads to a decrease in the partial pressure of carbon dioxide. So think of the lungs as effectively blowing off the excess acid in the form of carbon dioxide in an effort to normalize the body's pH. Now, in respiratory acidosis, we know that the pH is going to be decreased because we're in an acidotic state. And this time, since we're dealing with respiratory acidosis, we look at the respiratory component, which is the partial pressure of carbon dioxide. And so this accordingly will be increased in respiratory acidosis because remember that CO2 is acidic in nature. Now, in respiratory acidosis, the kidneys will respond by increasing the reabsorption of basic bicarb ions to try to balance out the increased acids. And so therefore the compensatory response is metabolic, and unlike respiratory compensation by the lungs, which is immediate, this compensatory mechanism by the kidneys is delayed. Okay, now on to metabolic alkalosis. In alkalosis, the pH will be basic, and so greater than the upper limit of normal, or 7.45. And since this is metabolic alkalosis, and bicarb represents the metabolic component, we know that this too will be increased, because again, bicarb is basic. And in metabolic alkalosis, again, the lungs can immediately respond by decreasing ventilation rate or hypoventilating, and this leads to an increase of PCO2. So the lungs effectively create a buildup of excess acid to try to counter the increased basic bicarb, again in an effort to try to normalize the body's pH. So the compensatory response is hypoventilation. And finally, we have respiratory alkalosis. So again, it's alkalosis, the pH will be increased or basic. And we're talking about respiratory alkalosis, so we look at PCO2 first, and we're going to account for the alkalosis by a decrease in PCO2. And again, the kidneys are going to respond by decreasing the reabsorption of bicarb ions in an effort to balance out the pH. So bicarb will decrease because of the compensatory response by the kidneys. So there are a few key things to keep in mind. Whenever you have an acidosis or an alkalosis, the pH will match up accordingly. Then, in both metabolic acidosis and metabolic alkalosis, primary disturbance is going to be in the bicarb concentration. So that will match up with the pH, and then the partial pressure of carbon dioxide will be a compensatory response, either hyperventilation or hypoventilation, and that is immediate by the lungs. Now, in respiratory acidosis or respiratory alkalosis, the primary disturbance is going to be in the partial pressure of carbon dioxide. It will correspond to the pH. And then the compensatory response will be the reabsorption of bicarb by the kidneys. And this response, unlike hyperventilation or hypoventilation, is delayed.